Hello. Today's session will be about applying artificial intelligence to incident response. And we're actually going to teach you how to do that in the different stages of the incident response. The agenda will include what is AI. We'll then talk more about how is AI related to IR, what is the theme, when is it important, and how to implement it. We're going to touch about investigation, going to touch about how to apply this to response, and of course, harnessing all of the above into the cloud, and we'll end up with takeaways. So briefing into AI. So AI is definitely a buzzword today, and there's a lot of items and buzz that are related to it, but machine learning is a subset of artificial intelligence. Not all artificial intelligence has machine learning. And the machine learning itself, we're going to talk about the different learning mechanism, but as a subset of machine learning, we're also going to talk about deep learning, which is going to be part of our session today. To understand machine learning in a high level, you need to understand how does it actually work. From a general point of view, the idea is to feed a system with data sets. Data sets could be positive, data sets could be negative, but we need to know the features that we want to extract out of the data set, the one that we actually going to be the junctions, the ideas that's going to determine the algorithm later on. And once we have those data sets and we understand the feature extract out of those data sets, we're going to teach the system, the algorithm, and create a model that from now on will be able to distinguish resembled data sets and be able to set them to the result that is required by those data sets. When we're talking about the methods of the machine learning, usually we're referring to two different aspects of learning modes: supervised and unsupervised. Supervised, and as you can see on the left-hand side of the screen, we gave a next generation antivirus as an example. Supervised means that you're giving a data set, as you can see in the example, that could be benign or malicious as a malwares. And we're trying to teach a function which is going to become the model into distinguishing between a malware versus a good file. And that is exactly the supervised model. So in the later stage, once the model is trained, we will push a data set that is unknown. And the idea is that the function, the model, will know how to set that and associate it into a malware or a benign file, where an unsupervised is more of a reference or a pointer into a specific kind of cluster. And then what we would like the machine learning to do is basically to be able to put the different data sets that's going to be fed into those classificators, into those data set clusters. And that's the idea about the unsupervised, providing reference and associating to the different references or families. Let's talk a little bit about another big term in machine learning after we learned the learning models, the reinforcement learning. What is a reinforcement learning? Basically, there are 4 different stages that I'm going to discuss here, but it all comes down from an agent, which is the tool that actually takes the action upon the environment. In our case, is going to be the enforcer, and the environment is going to be the incident that we want to deal with. Then what's going to happen is that the actions that's going to be taken by the agent is going to be then interpreted by an interpreter. The interpreter will try to better understand whether the action as taking on the environment was what we expected it to be or not. If it was the expected action, it will reward. That's why we like to call this model the stick and the carrot model. So it will reward the agent for doing the right thing. And of course, there is a penalty in case that was not the right action to take. And the state is actually the action that was taken, and after the action was taken, the impact on the environment. When we're talking about how to implement and how does it look for the internals, we'll talk a lot about trees and forests. And trees and forests, and in this example, for example, how to classify a file in a very high level and simplified model. The idea itself that what you see is the nodes that you see are basically the features that we discussed before. Those are the ones that we wanna follow. And each and every one of those features has a threshold. The threshold are the decision idea. So if the threshold can define what is going to be the left hand of it and what is going to be the right hand of it, is we're going to move around the tree until we're going to get to the leaf. which stands for the end result that we want to get. The idea, if you're looking at the right-hand side, is to have as many trees as you can, and that's why we call it a forest, where we can actually average and weight those trees, sometimes within machine learning itself, to be able to get ourselves a better and more factored result. Another big buzz in the learning and the models out there is using neural networks or deep neural networks. So DNNs and shallow network are the models that you're going to see there more and more. When again, if you're looking at the left hand, the inputs are the features. And the idea itself within the DNN is to try and imitate a human brain activity. And so the idea is that as an input feature, we're going into an inner tree, and the idea is to move between the different layers. If you have more than one and you're more than just a shallow and have a full, and it can have a lot of those layers, but the idea is to move between the features within the trees and move forward to the right next inner trees to be able to take the best decision. The more layers that you're going to have, in most cases, the better output, the more accurate the output is going to be. So just to summarize what we kind of went very quickly through here, on a high level, we talked about data sets, which is the data that we want to teach the model. We talked about feature set and feature reduction, which is the one that we want to actually learn the model. We talked about learning methods. So we were covering the supervised as the next gen AV, or the unsupervised as more of a classifying to families. We talked about reinforcement, the carrot model, and the models to use as implementation. We talked about the deep neural and random forest, which are very common to use. Each one of them, of course, will have its own challenge, and we'll talk about that. So you need to know what it's needed to use for. You need to understand that that's going to be an impact on CPU and memory and others. But now we're going to talk more about how to apply those into IR. So AI-based IR, what exactly are we talking about here? Incident response process. Let's go through the stages of the incident response. The incident response is built, as we broke it here, into 5 different stages. The first part is the preparation. What do we want to have? What is the, I would say, the best practice or the pre-canned concept that we want to follow? And then we're going to have the detection. So that's the initial incident that we're going to track. Once we have that, we'll move to investigation analysis in order to better understand what are we facing here. And once we understood that, we'll need to take an immediate containment in a, maybe sometimes a micro containment, just to slow down of what we're seeing. And then when we have that clear idea, we'll take a post-incident activity across the board and, of course, feed it back to the preparation. So for the next time, we'll be more adjusted and more tuned to what we need to have. Let's start now with the investigation, and then we'll touch the containment part and see how AI can actually apply to it. What is our goals here? The goal is first to understand and better classify what are we facing here. Is it a good one? Did we catch the needle and the malware, or are we looking into false positive or an incident that is still have not matured to become something? We need to scope it. What was affected? Which artifacts are related to the effect of what? We need to try as the source of where and how did it all start. So we need to have a better picture of what are we facing here. And we need to understand how fast do we need to remediate, which is going to be the next stage. And what are we using as a data source? Almost anything that can serve us within the environment. That means endpoint data, network data, intelligence, sandboxes, reputations, and of course, humans. We'll talk a lot about the fact that humans are needed in order to keep on tuning the system. Moving forward to containment, and that's, of course, already part of the immediate or part of the response. What are our goals? Our goals is to remediate. To remediate by meaning removing all traces of an activity that had consequences on the attack, and recover, meaning go back to normal, go back to business. When the input is our investigation results, which could be a lot of things there. And of course, the tools that we're going to use are related more to endpoints, network, physical, again, of what are we going to do with the machine. Sometimes you need to physically intervene in that, and mark false positive and other misleading artifacts as one, so we can actually do that better in the next cycle of an incident. So why do we actually need this? I think that goes without saying. We need to make a more automated incident response. We have a shortage in cybersecurity personnel, and time to response is critical. We all understand how fast consequences are happening, especially in a ransomware, but we need to move to a quicker and faster and also a scalable across the board incident response. And when we talk about how to do this, so I think when you're trying to correlate the AI-based IR, you need to understand first how to collect real-world attacks. So that's, of course, a data set that we'll need to train. But of course, with that, we also need to have the day-to-day normal data sets that are working and are not malicious, so we can train the other side of that as well. We need experts, humans, again, to help to teach the machine. Not everything is going to be done automatically from end to end, and the machine learning is not always going to be that tuned, and therefore we'll need people to tune down the models and tune down the inputs. And that brings me to the last point of just don't, I don't want anybody to expect that AI or in machine learning in specific are going to do a black magic here and completely replace our incident response analyst. It is not. So as you can see, a lot of human intervening is still needed. And then when going back to the data collection that we need to do, so we talked about building good data sets. These are the day-to-day, and these are the hardest to do because malwares and IOCs and all the rest of those are very available, but good scenarios that also could be related to one environment or the other are hard to collect. Different artifacts type, of course, when it comes to URL and behaviors, but the benign one combination with real world attacks and emulators are the main one to collect and feed the machine learning. Now we're going to move to teaching to investigate. I'll move that to you, Udi.
Okay, next up, teaching the machine to investigate. So this is the process that we have built to automate the investigation stage using machine learning. So it all starts with detection. Basically, we are getting some kind of information from endpoint or firewall that indicates that some incident occurred. The next phase is to normalize this data. So we will have it in a unified form for the next stage where we extract the different artifacts, whether it's processes, files, behavioral chains, or whatnot. Next, we will try to scope the incident. Scoping means that we will try to see everything that was affected by the incident. And the better we do that, the more accurate the response will be, and more on that will be discussed later. Next step is enrichment. During the enrichment phase, we will execute sandbox, check intelligence, and basically leverage everything in our disposal to get as much information as we can on each of the artifacts. The next stage is where machine learning or AI comes into play. And basically, we will classify each artifact and move on to another scoping phase where we will either remove or expand the scope of the incident based on the classifications. And I'll explain what I mean later, but basically, if we have new items we need to add, we will need to go back to the enrichment phase and again to classify the artifacts. If we are done and there are no more artifacts to analyze, then we are pretty much done, and we have classified artifacts we can work from. Normalization. So as mentioned, the goal is to have the data in a unified way. For example, if we have two SIEMs that we are using as data sources, we need to be able to use them both for the investigation. So the idea is that the rest of the system won't be affected by the way the data looks. AI is not really needed for this stage, and if you have your own systems or very specific systems, you probably don't need it at all. Extraction. So for extractions, AI may be beneficial. For example, getting URLs out of command lines may be useful, or registry keys from text and identifying those kinds of artifacts. We will not dive into these models due to lack of time, but just FYI, simple pattern matches can probably do a very good job at this stage, and many times there is no real need for fancy models. Okay, scoping. So as I mentioned, it has two main goals and stages in a way. First, the goal is to find what the incident affected. This will also allow us to triage the source, and we will see how it works later. And at this stage, we will also collect and remove artifacts, which allow us to get a better classification for the entire incident. As mentioned, it is executed before every analysis, and it is critical to ensure that we get the right context for the incident. So this is an example of adding an artifact to the investigation process. Let's say that we have identified a malicious process of one of the devices, device A in that example, and we witness it connecting to some malicious IP. Now, using some other data source, EDR or whatnot, we also know that process B from device B also connected to that IP. So it is very likely that this process is also related to the investigation. And so it will be added to the incident, and the investigation process will work on it as well. As an example for removal, we can see another situation where a suspicious process makes some malicious behaviors. So normally, we will also want to throw in the parent for analysis, because the parent might be interesting as well and might be the actual source of the incident. But let's say that reputation already knows this file and we know it is good, so we can remove it out of the scope of the incident, and we won't analyze it or look anything according to it. So this is a way to reduce the scope of the incident and focus on what matters. Enrichments. So here we pretty much use every data source we can to make the investigation as accurate as possible. YARA rules, environment-specific data, like when a file was first introduced and stuff like that. It can also involve getting unknown files from endpoints or memory dumps. But one of the most important points here is that we should also be able to add a rule engine at this stage. The idea is that machine learning, as good as it's going to get, it's never going to be able to handle all the unknown behaviors out there and emerging threats. And having a rule engine that a human can tweak will allow us to overcome such issues by quickly adding new rules that indicate that something bad is going on. I think that the recent Exchange exploit is a very good example of that. I'm pretty sure now pretty much every vendor added dropping of new ESPX files as a suspicious behavior to their EDRs. Okay, all of those will be added as features to the models. Okay, so classifying artifacts. In this presentation, we will focus on static file classifier and process behavior classifiers. Other common classifiers are domain name or user activity classifiers, which are used for UEBA products, but due to lack of time, we won't cover them. Other artifacts like IP don't necessarily need classifiers. Stuff like intelligence is probably good enough for them. Okay, static file analysis, or classification. We touched on that a bit on the first slides. So basically, we take malicious files, good files, extract features, and train a model. One good thing about files is that there are a lot of sources, and VirusTotal is a very good one. You have a lot of labeled data, which you can use to train the models. Some feature example, entropy, is it signed or not, import tables, and so on. But the key thing here is we also have domain knowledge experts in these stages to be able to choose the features right and to do a feature selection. We won't dive into that process, but it is important to note that as well. So our strategy was to build two models, actually. One for the endpoints, where we use the random forest, very small, less than 10 megs in size, and also super fast, less than 10th of a second on average scan. A few updates are needed once per quarter, and it's quite accurate, 93%. The cloud model is using deep neural networks. It's over 1 gigabyte in size and is constantly being trained for millions of samples. And while the difference in percentages doesn't seem like much, consider how many files you have in an organization and how much 1% really mean. It's actually real world accuracy here, not like something that was fetched from some learning algorithm. Okay, so process behavior classifier. Here we need a more complex learning algorithm, and we use pseudo-labeling for first stage. So the idea is to take both good and bad behaviors, we got them from emulators and sandboxes, and train the first model very similar to the way we did in static file analysis. Next, what we do is take unlabeled data. We have tons of that on real-life environments, and we feed it to the model, out of which we get new data, actually not new data, but new labeled data. Some labeled with high confidence, according to our models, and some labeled with low confidence. We take the data that is labeled with high confidence, either as good or bad, and add it to the data set. Obviously, human is part of that cycle too, just to make sure that what we are adding really makes sense, and whatever is added is good, and whatever is added is bad. So once we have that, we basically have much bigger data set where we can train again and create our final models. Obviously, there are many iterations. It's not a single iteration, but that way we are capable of building a much more accurate machine learning model. Another technique we used is called GAN. Basically, what we have is adversary model that tries to generate behaviors that will make our initial model fail, either by making the wrong decisions on malicious behaviors or on good behaviors. And doing many iterations of that and training both the adversary and our model that means to classify good and bad behaviors ensures that we are getting a much more accurate results in the end. There are different features for behaviors, injections, dropping of files, encryption of data, and so on, but the general idea is the same. Here we also use the cloud model, again, very big, over a gig in size, which is constantly being trained from the live data and from emulated data. We also use specialized model, for example, for processes like PowerShell. And the accuracy here is really hard to measure. And the reason I didn't put like 99% here or something like that is because you will always get a kick in the face kind of when facing real world environments. And you'll find new things that are good, that are doing things that look very malicious, and things that are bad that you haven't seen before and no one saw before and might be missed. Okay, so a bit about triaging. So if we have a very good investigation, we will also have a very good triage. And as an example, let's consider a scenario where we detected some zero logon exploitation attempt on one of the Active Directory servers. From that point, it is also possible to trace it back to a connection to the machine where the attack started from. And it's also possible to identify the session and from there move to another server that was before that logged in by an attacker using RDP. All that is possible if you have the evidence. The more data sources you have, whether it's from the endpoint or firewall, the better triage and scoping is possible. Okay, so to sum this part up, automated investigation is complex and humans are needed. But obviously, if done well, it will save endless man-hour. You don't have to develop everything at once. You can deploy it gradually. And as we will see, it is the key for good responses. Okay, but remediation is mostly easy because let's say you have a bad file, delete it. If you have a bad IP, block it in the firewall. A bad process can be terminated, suspended, maybe remove the file too. And if you find infected device, we can always just quarantine it. But it is not always that trivial because maybe randomness is introduced. For example, let's say the attacker is using a legitimate website, then we don't want to block the domain. And if we have another case where randomness is introduced to the URL, we don't want to block it based on the full URL, because in that case, we won't really block anything because the next binary will have a different number and it will still work. And generally, machine learning and AI will easily be able to handle the easy cases as well. So adding those capabilities will only improve the response. So this is the process we have built. It's quite simple. We get the classified artifacts from the investigation, put it into the response model, which generates recommendations or actions that should be executed. Based on certainty thresholds, the machine will decide whether to execute it immediately or just recommend it to the analyst. And then the analyst can provide feedback back to the machine by either approving or disapproving the actions and recommendations, which will enable learning of better models in the future. So using semi or full automated response. So it is hard to tell, and a lot of tuning needs to take place in order to get it right. Since some actions can be extremely destructive, for example, quarantining a server because some PUP is running is probably going to cause more damage than good, which means that we will probably need some rules here as well, like never quarantine some machines. And some of the models will probably needs to also control how fast we need to execute actions. For example, if we see that it is a ransomware, we need to take actions as fast as possible in order to contain the threat. So we won't be able to dive into the exact model here, again, due to lack of time, but the sources are pretty much similar. We used real-world scenarios, sandbox data, and emulators, and also DNS and URL data from intelligence. And there are multiple models here, but some examples that we are using is URL response models which tries to decide which part of the URL needs to be blacklisted or whitelisted if needed. And also another one to decide what's need to be done to remediate a threat. Okay, to summarize, the key to good response is good investigation. It highly depends on how good the investigation models are. And the feedback design is critical, and I will dive into that in the following slide. So how do we apply all that to the cloud? So this is the architectures we were using. So we have all kinds of data sources, the firewall, EDR, and so on. And we push that data into data queues. Those queues lead to our normalizer, which pushes the data into a big data repository. And once we get there, investigation can begin. The investigation leverages sandboxes, the classifiers, intelligence, and everything at our disposal to get a good classification and scoping for the incident, which is later fed into the response, the automated response model, which will orchestrate the deletion of files, quarantine of devices, and so on. But this is also fully integrated to MDR console, which allows humans to interact with the response and also create feedback for either bad or good responses and investigation results, and therefore allowing us to keep improving the system. So some quick recommendations. Kubernetes is awesome for scale. You can grow big as you need to handle more and more data. You should streamline the execution for queues. RabbitMQ or Kafka are good, so you'll be able to control priorities, and also to reduce data reduction in case something breaks down. Also use existing tools where possible, stuff like Redis for caching and so on. And how all this relates to AI, you may ask. So as I mentioned, we also need to be able to constantly improve. So MLOps is the key to that. And the way we did it is to take extracted items each time a new investigation is being handled, and not only send it to the current models which actually handle the automation. We will also send this data to new models we are trying to build and measure them. And each time we get new results, we can compare them based on the feedback we are getting to what we actually got in the automated process we currently have. And now when we manage to create a new and better model and replace the current one, and this cycle goes on and allows us to create a much better response and investigations. Some tips: conduct full research on the infrastructure. It will bite you if you don't. MLOps needs to be planned from the get-go, and be sure that your first models will probably be bad. Thus, the ability to constantly improve them is the key here, and being able to measure everything is another key to make sure you are able to build the best possible machine around it. Also, you must use a mix of domain experts and data scientists. Only one will not do, simply because the best way to build great features are the domain experts. And obviously, all the learning algorithms and models and measurements are better be done by scientists. So, takeaways. Machine learning is a hot subject and is being applied to more and more domains in the cybersecurity, but it's not going to replace humans anytime soon, at least. That said, it is a great tool to complement IR and save human resources, but it's also complex and requires a lot of domain knowledge, and it's very hard to do as a typical organization. And the end goal should be not to automate everything, but to automate what's possible and to provide the incident responder as much data as possible to take correct actions when it's not possible to automate. There are obviously other ways to do that. What we provided is how we did it and the experiences we had when building such a system. Also, some other sources you might find interesting. And that's it.